Welcome to the Explainer. Whenever we look at a set of architectural drawings, it's so easy to just see a staircase as a series of neat parallel lines. But as quantity surveyors and estimators, we know the real truth. A staircase isn't just a set of lines on paper. It's a complex, three-dimensional structure that bridges the gap between abstract design rules and hard, expensive concrete volumes. Today, we're going on a bit of a journey. We are going to transform those architectural lines into a highly accurate Bill of Quantities, or BOQ. We'll start out with the historical geometry of human comfort, navigate through some strict building codes, and ultimately end up with the exact concrete and formwork calculations you need on the construction site.
Okay, let's dive right into this. Here is our structured design-to-delivery roadmap for today. First, we'll look at the geometry of safety. Second, we'll compare residential versus public parameters. Third, we'll discover exactly why the riser dictates everything. Fourth, we'll break down the incredibly useful split calculation method for concrete volume. And finally, we will wrap up with the realities of the site, like formwork, wastage, and finalizing your BOQ.
Section 1. The geometry of safety. The foundational rule of stair design.
Before a staircase ever becomes a calculated cost of concrete and steel, it absolutely has to be designed for human comfort and safety. Think about it. If the geometry is wrong, the entire staircase is just one massive tripping hazard. And as an estimator, you really need to understand the constraints the architect was working under, mostly so you can spot potential errors early on. This brings us to a foundational rule that is actually still embedded in modern building codes today, Blondel's formula. The formula states that 2 risers plus 1 tread, which we also call the going, should equal roughly 25 inches. That translates to an allowable range of about 550 to 700 millimeters. Why? Well, because the average horizontal stride of a human is about 24 to 25 inches. If you're stepping upwards, you naturally have to reduce that horizontal distance. By factoring in double the vertical rise, the formula inherently limits your stride length. It's essentially a geometric boundary, so people aren't forced to take tiny, awkward stutter steps or overly large, unsafe strides.
The origins of this are just fascinating. François Blondel, a 17th century French architect, understood the importance of comfort in stair design. This formula is a golden rule in architecture. It's actually pretty wild to think that as a modern QS, when you're pricing out the cubic meters of concrete for a massive high-rise core, the foundational dimensions you are measuring were actually standardized by a French architect over 300 years ago just to match the natural human gait.
Section 2. Residential versus public parameters. Applying the code to different building types.
Now, what's really interesting about this is how Blondel's formula, which gives us a range, actually translates into strict modern legal requirements, and it heavily depends on the user. Notice the stark contrast between private and public requirements, like what you'd see in regulations such as Approved Document K. Just look at the maximum rise. For a private residential stair, you can push that right up to 220 millimeters. It can be significantly steeper, up to a 42-degree pitch, simply because people are familiar with their own homes. But then look at general access or public stairs. The absolute maximum rise drops to 170 millimeters, and the minimum going extends out to 250 millimeters. The code strictly demands shallower, wider steps for public buildings to protect users who are totally unfamiliar with the space or who might be navigating in heavy crowds. As an estimator, knowing these code limits is a superpower. It means you can immediately flag a design that specifies, say, a 200-millimeter riser in a public commercial space well before you ever start pricing it.
Section 3. The riser dictates everything. Finding the master variable.
All right, so let's shift our mindset from architectural rules to the actual mathematical calculation process. When you sit down with a fresh set of drawings to start your takeoff, where do you begin? Why is the number of risers our master variable? Just think about this for a second. Out of all the dimensions, the going, the width, the landing length, why does the estimator's job absolutely always begin with calculating the number of risers?
Well, it all comes down to this equation. Total rise divided by maximum legal rise equals the minimum number of rises. You see, the total rise between floors is a fixed, non-negotiable physical distance. You literally cannot change the floor-to-floor height. So by taking that fixed total rise and dividing it by the maximum allowable riser height from the building code we were just talking about, you find your minimum number of steps. If the math spits out a fraction, you always round up to the next whole number, which slightly lowers the actual riser height to a safe, compliant level. And once you have that final number of risers, everything else just cascades from there. It unlocks the minimum required going, which then dictates the total length of the staircase footprint, which directly determines the ultimate volume of your bill of quantities.
Section 4.
The split calculation method, deconstructing the staircase for concrete volume.
Let's move on and see how this builds right into the hard math. We know our dimensions, sure, but how do we accurately calculate the concrete volume without getting completely lost in that complex zigzag geometry? Think about a standard plan view of a dog-legged staircase supported on 300mm walls. To a layperson, that looks like a single continuous pour, but to an estimator, trying to calculate that as one giant shape is a total nightmare. Instead, we use the split calculation method. We essentially mentally deconstruct the staircase into 3 distinct, highly measurable components: the landings, the waste slab, and the triangular steps themselves.
But before we can measure the waste slab, which is that structural spine running right beneath the steps, we have to know its thickness. Notice how a structural engineer determines the trial depth using the effective span and loading requirements. The distance between the supports, combined with live loads and finishes, dictates that our waste slab needs to be, say, 230 millimeters thick. As a QS, if the waste slab depth isn't explicitly detailed on the drawings, you absolutely must understand this engineering principle to estimate a safe assumption. Otherwise, your concrete BOQ is going to be dangerously underpriced.
So here is the exact QS workflow for the split calculation. Step 1, the landings. These are super easy. Just treat them as flat rectangular concrete slabs. Length times width times thickness. Done. Step 2, the waste slab. Now this is the tricky part because it slopes. You cannot just use the horizontal length on the plan. You've got to use the Pythagorean theorem, where the total going is your base and the total rise is your height, to calculate the true sloped length of that waste slab. Then, simply multiply that by the width and the thickness. Finally, step 3, the steps. We've already accounted for the slab beneath them, so the steps are literally just simple right-angled triangles sitting on top. Take the area of one triangle, half the going times the rise, multiply it by the stair width, and then multiply by the total number of steps. Add those 3 components together, and boom, you have your exact theoretical concrete volume.
Section 5. Formwork, wastage, and BOQ. Finalizing the estimate with site realities.
We have our pure geometric volume, but as we all know, construction happens on a messy, imperfect site. Let's bring this calculation home to reality. So the crucial point here is visualizing where the money actually goes. In a typical example of a 1.555 cubic meter staircase, just look at the distribution. The waste slab eats up nearly half the total concrete volume at 0.656 cubic meters. The landings take up another large chunk, and the actual triangular steps themselves are just a small fraction of the total volume. If you miscalculate that sloping waste slab by forgetting the Pythagorean theorem, your estimate will be drastically short.
All right, time for an Info Engineer pro tip. Don't just take that pure geometric volume and blindly drop it into the BOQ. You must account for the volumetric conversion factor, or VCF, to translate those dry materials into wet concrete. And listen closely to this. The base VCF is not a constant. Modern site data shows that variations in the water-binder ratio heavily impact compaction efficiency and the final volume. You have to adjust your BCF for this. Furthermore, staircases are notoriously difficult to cast. You must add appropriate wastage factors, especially if the design calls for complex sliding, climbing, or highly detailed stepped formwork. And speaking of formwork, remember that the standard method of measuring dictates that the sloping soffits, the vertical risers, and the outer edges must all be measured and priced as completely separate formwork items.
We have covered a massive amount of ground today, from a 17th century French architect's rules on human gait to the strict limits of approved document K, through the Pythagorean split calculations right down to the site-level water binder ratios. So I want to leave you with this final thought. The next time you look at a set of staircase drawings, don't just see lines. See the structure, see the safety, and see the exact cost. How will you apply Blondell's logic to completely master your next estimate? Keep learning, keep analyzing, and we'll catch you on the next explainer.